Before I introduce an old friend of this community, Iwarmura-san, I'd like to say a couple of things before you talk, and it won't come out in time because we're a little bit ahead of schedule. Microphone. Can I borrow that? Is that better? Dr. Iwamura has been presenting at these meetings for years, and some of the work which led to the exchange of views this morning between Iwamura-san and Dr. Kidwell is part of an ongoing conversation now. I believe it's going on, what, 8 years, that conversation? And I consider it, I mean, both of these people are very fine scientists. Both of them have done extraordinary work. The team that was put together to understand and examine the work at Mitsubishi was fortunate in being sponsored at a level such that we could do a pretty decent job. The cooperation of Iwamura-san and his corporation is something that was one of the more satisfying experiences in the scientific businesses that I've ever had, because we had access, basically open book access, to not just the work that was talked about today, which is a very limited part of Iwamura-san's work. We worked with him for approximately 2.5 years, starting off slowly, and then continuing for 3.5, 4 years, and then the conclusion that was given by Kidwell today is right on the money with respect to a set of work that we did with him in his laboratory and analysis techniques which were developed by NRL. There was a wide body of experimental work beforehand, which included 180 some odd experiments in which Iwamura-san used ICP-MS to measure the production of praseodymium in his experiment. And we had access to about maybe 4 or 5 of those foils before we started into this work. We analyzed it. Kidwell mentioned that we used the accelerometer mass spectrometer to ascertain there was praseodymium on the sample. The way the project was set up involved a red team which had some very capable people in it. And I want to commend Iwamura-san for basically taking the board, arguing vigorously with us about what we understood, and continuing his work. And I hope it was a useful experience for him as well. So this is a little longer than what a moderator is supposed to say, but having spent 11 years working on this, I feel I get a couple of minutes. So Iwamura-san, thank you.
Okay, today I would like to talk about the recent advances in permeation experiments. First, as you know very well, conventional transmutation requires a very large accelerator or nuclear reactor. But our method, permeation-induced transmutation method, requires a very compact and low energy device, because this phenomena is induced under about 60 or 80 degrees and only 1 atoms of D2 gas. And using our original structured palladium and multilayer. Okay, so I will explain the feature of our method. Our method is characterized by a D2 gas permeation through nano-structured palladium complex. This is a cross-sectional view of our multilayer thin film. And this black region corresponds to the palladium, and the white region corresponds to the calcium oxide. calcium, the thickness of the calcium oxide is about 2 nanometer, very thin nano range. And palladium is about 20 nanometer, and the surface is a palladium 40 nanometers thickness. And before D2 gas permeation, we put elements which we would like to transmute on the upper side of the multilayer thin film, like this. And we provide D2 gas on the top side, and we keep vacuum on the other side. Because the palladium has a nature that hydrogen or deuterium gas easy to transmute, easy to absorb. So the permeation occurs like this. And then we can observe these elements in advance we put can be transmuted to another element. That's our method. So this is a transmutation of example of transmutation of cesium into praseodymium. This is our apparatus. At the beginning of the permeation, we only have a cesium here, but as time passes, as deuterium gas through the multilayer, cesium decreased, and the correspondingly praseodymium increased like this. And this is summarized observation reactions observed so far in our laboratory. In MHI means Mitsubishi Heavy Industry. Transmutation of cesium into praseodymium is confirmed by many researchers, and also we have many experiments for this reaction. The other reactions, confirmation, number of confirmation is limited, but we observe these elements transmutation. And if we put these elements on the periodic table, we can see that alkali and alkaline metals tends to be transmutatable by our method. And the other feature you can see that cesium and praseodymium, we need a 4D. Cesium plus 4D get the praseodymium. And the other elements also 4D or 6D and 2D and 4D. Up to now, we observed the 2D and 4D and 6D reactions using our method. Okay, and this is a potential application using permeation-induced transmutation. First one is nuclear transmutation of radioactive waste. For example, cesium-137 can be transmuted by this method. And the other is production of rare metals. We observed this transmutation of tungsten into platinum. So it's like alchemy. And the third one is a portable nuclear energy source. Because these reactions, all these reactions are exothermic reaction, heat release reaction. So we can use this transmutation reaction as an energy source. Okay. So this figure shows the key factors in permeation experiments. We assume that that's a hypothesis at present. We assume that the local deuterium density is very important. So high deuterium density is preferable. And the electronic structure also important, we think. And yes, and today I would like to talk about the recent advances using electrochemical permeation. I presented at ICCF this kind of permeation method. And today, I'd like to explain about the transmutation products confirmed by XPS and observation of gamma ray peaks. But the gamma ray, we observe gamma rays, but the reproducibility is not high. Maybe this gamma rays peaks are induced by the increase of transmutation products, because we aim that this method, electrochemical permeation method, we aim to increase the transmutation products. Okay, so I will explain. This data shows a praseodymium dependence on D2 gas pressure using gas permeation. This side means conversion rate. Conversion rate means how much portion of cesium transmuted into praseodymium. This side is the amount of praseodymium per nanogram per square centimeter. We usually use palladium sample about 1 centimeter, one square centimeter. So this is the real amount of praseodymium. And blue point, the results of relatively low pressure, about 1.2 and 1.3 atom. And the red one corresponds to the relatively high pressure, 1.8 and 2.3. So you can see that the pressure, if we increase the pressure, praseodymium increase. So if we use a high pressure D2 gas, we would get a match praseodymium. But it is very difficult, very high D2 gas environment, and in the view of safety experiments. So we try using this method. Usual gas permeation, I explained, it's an original model. And recently, we introduced this type of permeation method. In this case, we use D2O solution instead of D2 gas. And we electrolyze D2O, and D2 gas is generated on the surface. And after that, the D2 is decomposed into D atom and permeate. The other is the same. So gas permeation and electrochemical permeation is essentially the same, but the different point is how to produce a D2 gas. Okay. This is a figure of our apparatus. Experimental apparatus aiming increase of D density. Because electrolyze, if we apply this technique on the D2 gas, equivalent D2 gas pressure goes up. So we would increase the D2 density, very high density on the surface. Okay, so I'd like to present about the observation of gamma ray peaks. This is the reactor cell, and this is a germanium detector for gamma ray measurement. And we measure, recently we always measure using this germanium detector. And this is an example of gamma ray detector detection of E16. This is the time, and we provide a voltage. At the beginning of the experiment, we provide 3 volt and 4 volt, and we increase up the voltage. And this red line means current. And And this pressure means here pressure. So this pressure means permeated D2 gas pressure. So this red line corresponds to the current, like this. And in this case, we use palladium Y2O3, not calcium oxide. And beforehand, we put the cesium by ion implantation method. And we use a 0.5 molecular mole C2NO3 D2 solution. And we provide period 1 and period 2 and period 3, and we also, of course, a background measurement before and after this experiment. During the period 1, we observed this gamma ray peak, like this. And the period 2, this one is vanished, and instead, gamma ray about the 511 peak. And period 3 also we measure this one. And summarize, period 1 we detected a 609.5 kilo eV gamma ray, and the period 2 and 3 we get this gamma ray. And these data are presented at ICCF-18. And after that, we measure the sample for E16. And this is a result of analysis of E16. This red one means correspond to the E16 permeated region. This is our sample, and these are permeated region. If we analyze the permeated region, we can see the clear praseodymium XPS peak. And this is data from the no permeation data. We measured for this sample H region, and also we do not have a praseodymium, so we can conclude that for the permeated region, we can detect the praseodymium. Okay. The next example for gamma ray. This one is using calcium oxide. This is wrong, calcium oxide in this case. But we have no cesium implantation beforehand. And we also divide the period 1 and period 2 and measure the background. In this case, the other energy gamma rays we detect. Black one is period 1. Period 1 means this region, and red one is period 2, and green correspond to background. And we plot for these 3 periods, and we can see that the clear gamma ray peak for about 1445 kilo eV. Oh. And also we can detect 1745 kilo eV, and the other small one 507 and 578 605 gamma ray for period 1 only. Oh, and the other peaks. So summarize, detected gamma ray energy is like this, and count per sec for this sample like this. And we try to explain these gamma rays, and we searched gamma rays from unstable nuclei and excited nuclei and some neutron capture gamma rays. But up to now, we have not succeeded to find a nucleus fit for the observed gamma ray energy. So we need a further study The first one is a replication experiment and build a physical model for this gamma ray observation. Okay. Next point is recent analysis using ICP mass and SIMS and XPS. This data also we presented at ICCF-18. This is using SIMS analysis. This red one corresponds to the center region. That means a permeated region. And edge region, corner region is green. In this case, we provide cesium ion implantation beforehand. So same level of cesium exists before permeation. So, but after permeation, this cesium decrease like this, and correspondingly increase around mass 60. We can observe like this, and okay, and this is the enlarged spectrum for around mass number 140. And we can see this increase of the D's as same spectrum. And we confirm by this result by ICP mass, and also we get a very similar results, very similar spectrum like SIMS and ICP mass. Because SIMS is a point method, only point data we get by SIMS. But ICP mass is not all surface, but this surface. So I think that it is relatively reliable. And we apply this sample XPS. In this case, praseodymium peak is not so strong, but we confirm the praseodymium by XPS. Okay, we summarize our results. We applied an electrochemical method to increase deuterium density near the surface of the palladium multilayer thin film, and transmutation product increased, and gamma rays occasionally detected. And this chart shows the comparison between gas permeation and electrochemical permeation. Before 2010, we get the praseodymium around the nanogram order, but recently we get the more transmutation products. Okay. Now we conclude low energy nuclear transmutation from cesiums and the others have been observed in palladium complex. And the electrochemical method was applied to increase the local deuterium density near the surface. And we get about 1 microgram per square inch by this approach. And the statistically significant gamma rays, which have clear energy spectra, were detected. These emissions were supposed to be caused by the increase of the transmutation products. At present, we have limited examples. Further study is necessary. Thank you. Thank you for your attention.
You seem to have been using natural cesium in all of your work.
Yes.
Have you checked to see that it works with masses like 137?
Radioactivity and cesium. Yeah. We perform this kind of experiments, and we observed the decrease of gamma ray from cesium 137.
I was wondering if there's, with the rapid increase in the production rate that you showed in your last slide, is there would there be, say, an opportunity to try to isolate the product and, by chemistry show the increased density of the product?
So you mean the confidence of these.
Well, is there a chemical process? I'm sorry. Is there a chemical?
Is there a chemical process by which you could, in fact, isolate the product you've created?
Chemical. You mean? Sorry, I can't understand what you mean exactly. So you mentioned about if these are chemical reactions.
No.
Can you increase the production rate by doing chemical processes on what's on the surface?
Or can you extract from the surface?
Oh.
Can you refine the product off of your process?
Concentrate to.
To raise it from 10 nanometers to 100 nanometers, nanograms. Can you do a chemical concentration?
Chemical.
Chemical effect. You mean?
Chemical extraction.
Okay.
Chemical isolation.
Chemical isolation of the product. Chemical isolation for praseodymium and other elements.
Could you get cesium-137 out of this mix of stuff which you have on the surface there, for example, if you had cesium-137, so that the process that you're driving for, which is a way to treat radioactive waste, you would have the next step, so you would have a very small quantity.
Okay, I got it. Sorry, it takes a long time. So.
Sorry.
We do not yet about isolation, chemical isolation, but it's a practical problem because chemical process for radioactive waste. That's a very important point. But we do not yet perform. But somebody other section trying to make up this process. Yeah.
Maybe,
Yes.
You use?
When it's ready, it's good.
Very good. Not very good. Yes.
Okay.
Okay. So, it's a way I can reconfirm the data of Iwamura, because about 10 years before we make experiments using special electrolysis with strontium salt, and we increase a lot the production of molybdenum. But because it also can be some contaminations in some way, after 2 years we have to stop the experiment. Anyway, with electrolysis, the rate of transmutation increased a lot. So I agree completely with Iwamura result. We used pulsed electrolysis, special concentrate, but the trend is the same.
Okay.
But our system, for some reason, we are not able to make very good result with cesium, because our process works with alkaline-earth material. But with strontium works really well, and with barium even better.
Thank you.